Hi there, welcome to APES Chapter 18, lecture video number 1. This is the chapter on climate change, global climate change. So we just wrapped up Chapter 17, which talked about weather. Now we're going to talk about climate, which is what you expect your weather to look like. So let's begin. First off, let's define climate. Well, weather is what you would expect uh, today's forecast to be, whereas, weather is what we get. Climate is what we expect. That's a better way of looking at it. For example, San Diego has rain sometimes. Our weather recently, when I'm making this video, we had rain recently. Do you expect rain in San Diego? No. Even in February. In February, we do not expect rain in San Diego. Doesn't middle of winter, you think that's a rain expecting month? San Diego has generally really clear blue skies in February, actually. So our climate here is what we expect. It includes how much rain, what the temperature is, the wind. They call it relative humidity. That's given the air pressure. This has to do with our last chapter. Remember, things move from high to low air pressure. That's all related when we talk about climate. Global climate change. Well, we have monitored the Earth for a long time and we are noticing patterns. The climate is changing. We are on a warming trend around the world overall. Right? They used to say global warming. People are still using that term. But the more, I would say, politically correct term nowadays is climate change versus saying just global warming. For some reason, you say global warming and it offends people. And I don't know why. Um, Earth, though, our climate, it's it varies. There's things that affect climate naturally that make the Earth cooler and warmer at different times. So we're going to discuss those things, and we're going to talk about what is happening on the Earth due to the current trends in global climate change. Three major factors that influence climate, huge factors. The sun, because this provides the warmth, the light, the radiation to keep the Earth the proper temperature. The atmosphere, without the atmosphere, we won't be able to trap in any of that warmth, and the Earth will be way too cold or be fried by too much radiation from the sun. And the oceans, they're so huge. 70% of the Earth is ocean, therefore, a lot of heat is transported around the planet in that water. So oceans transport that heat. The atmosphere can trap that heat and keep the Earth a moderate temperature, and the sun's energy is what we need to basically keep the Earth the correct temperature. If we were too close to the sun, it would be dangerous. We'd be too hot, too much radiation. It would burn off our atmosphere. So this isn't mentioned here, but part of why our climate is the way it is how far we are from the sun is a big factor in all that too. So let's talk. You hear this term a lot, the greenhouse effect. What is the greenhouse effect? Well, first off, let's talk about what a greenhouse is. Greenhouse is a house that looks like this, and there's these plexiglass type of walls and ceiling, and this is generally sealed. So there's an open door here right now. Inside of a greenhouse, you put plants in there. Greenhouses, you can have a greenhouse in a cooler climate, but inside of your greenhouse, you will notice it is generally warmer. If you've ever been in a greenhouse, you will know what I'm talking about. I got to experience this when I was a student at San Diego State. I believe I entered a greenhouse. It was during the winter time. It was a sunny day, a typical sunny day in San Diego, a 75-degree day in San Diego, sunny and nice. And you can typical day as we expect. And I walked into a greenhouse on San Diego State's campus in one of my classes, and it was very hot and very humid inside of that greenhouse. It was warm in there. So what happened? Well, that greenhouse is exposed to sunlight. Sunlight can penetrate these glass partitions or these plexiglass partitions in the greenhouse. So light can enter, right? Radiation enters. It touches the plants, it touches the ground, it touches everything inside of the greenhouse. And that light energy, the radiation that was light, gets converted into what's called infrared, which is a fancy name for heat. All right. So the light that enters has a lower frequency or a shorter wavelength of light. That energy gets converted into another form called infrared, which has a longer wavelength of light, longer wavelength of energy. And then that infrared, that heat, is now trapped behind all this glass partition of the greenhouse. So the inside of a greenhouse will be warmer than the outside temperature. You guys have this happen to you all the time in your car. Let me explain to you the greenhouse effect with your car. Your car sits in the sun on a warm day, in, let's say an 80, 85-degree day at Valhalla High School. You come out to your car at the end of the day to get in your car and go home, and you open your door. And remember, it's about, let's say, 80 degrees out. You open your car door, and it's about 110 inside of your car, 115 inside of your car. Well, if your car's sitting in the sun, your car has glass, which, glass windows, glass windshield. So light can penetrate the glass on your car like a greenhouse. Then that light touches the upholstery, the dashboard, the seats of your car, and it gets converted into infrared. Same thing happens. Now that heat is trapped behind your closed windows, you're trapped, your doors are shut. So now that heat just builds up and builds up in your car as the day goes along, and your car gets very hot. That is the greenhouse effect in your car. Well, the same thing happens to the earth. The earth doesn't have glass around it, but the earth has air around it. It has an atmosphere. And you got to think, some of that atmosphere is like, it's like glass. Light can go right through that air, those air particles, right through, just like it goes through glass. It touches the earth. That light energy gets converted into a longer wavelength form of energy called infrared. Now, it's kind of like that air around the earth. It's kind of like glass around the earth, and it's trapping the heat from going back out to outer space. And it's re-radiating that heat back towards the earth. And things that do that, they're called greenhouse gases. They're generally gases that are made of 3 or more elements, and they're compound. Good example, CO2, methane, N2O, nitrous oxide, ozone, which is O3. So if it has 3 or more, it is considered what's called a greenhouse gas. It is a gas that can trap and re-radiate heat back towards the earth in the lower atmosphere. So you got to think of the air around the earth, the atmosphere. It's kind of like glass of a greenhouse. Light can enter, and then it can trap it, just like the way a greenhouse would trap that heat. So we say, what's making the earth warmer? The greenhouse effect is making earth warmer. Right? This is a picture in your book. It's kind of complicated, and I have seen pictures on an AP test before. So let's talk about what these numbers mean and what you need to get out of this picture. These numbers have to do with units. So these numbers, the units for these numbers are watts, which is a measurement of energy per square meter. So whenever you're given units of energy per square meter, you're talking generally about climate change and how much energy is coming in versus how much energy is leaving. Ideally, the earth is in balance for the most part. So if we don't mess with the earth, humans are not involved, about 340 comes in from the sun, 340 watts per square meter per day. This is, I believe, in a 24-hour window of time. And you don't have sun the entire 24 hours. And I believe these numbers were calculated assuming you were at the equator at an equinox, which is equal day and equal daylight to equal night. So these are the numbers affiliated with equal day to equal night at the equator. So every square meter in a day gets about 340 watts of energy. Okay, on the earth, every square meter of the earth gets that much. If the earth was balanced, about 340 should be leaving. Well, look, 100 gets reflected out from the atmosphere. So 100 of it is gone. And then a lot of it hits the earth and gets outgoing. Remember, outgoing long wave because now it's infrared. So outgoing infrared radiation in the form of about 239. 239 plus 100 is 339. It's about a wash. So the earth, if left in balance, has a wash. Okay. So about 340 comes in, about 340 goes out. This is if the earth was in total balance. We don't have greenhouse effect in play. We are not gradually getting warmer. We are not getting cooler. We are staying the same way we are daily, and this is what we would expect. But due to the greenhouse gases in the atmosphere that trap things, a lot of this infrared radiation gets emitted back and causes the earth to gradually get warmer. These numbers down here, 342, 398, these are large numbers, and I'm not going to make anything up here. I do not know exactly what these numbers are referring to. I believe these numbers are referring to the potential of how much infrared could be, for example, radiate back to the earth. And it doesn't make a lot of sense to me because if 340 comes in per day, how is 342 emitted back? Those numbers don't quite click for me, especially these numbers down here. Okay, so I'm not going to give you a test question about something going on here, but I'm telling you, you'll see diagrams like this on an AP test. Make sure you understand what these numbers mean. Energy, watts per square meter. Okay, so this is balance. 340 in, 100 plus 239 out. That's balance. But the Earth isn't doing that because these gases are re-emitting radiation back. And remember, they come in as a short wave of light, and then when it hits something, it gets converted into a long wave of infrared radiation. Infrared is heat. The greenhouse gases, these are the gases in the lower atmosphere that absorb that heat and re-emit it back towards the Earth. Here's an example of carbon dioxide, water vapor, methane, ozone is another example. Nitrous oxides are another example. The most abundant one in the atmosphere, the one that we have the most of it, is water. Without water in the air, the Earth would be a very cold place. The one that's, and remember, water is the most natural, abundant one. The most abundant one due to anthropogenic causes, human causes, is CO2. So the greenhouse gas that's doing the most problems, causing the most issues right now, it's not water. Water is naturally there. The greenhouse gas that's causing the problems in the earth is carbon dioxide. We are creating a massive imbalance. We are producing a lot of it daily, and we are way out of balance with our CO2 production. Water is the most abundant, but not the problem of what's happening. The problem is CO2. So CO2, most abundant anthropogenic greenhouse gas. Global warming potential. Well, not all gases have the same ability to absorb and re-emit the heat. Some are better than others. We measured them all against carbon dioxide. Carbon dioxide gets a value of a 1. Okay, so the potential for carbon dioxide to heat is 1. Well, it's nice because it's the lowest value, which means it has the lowest heating potential. But the problem that it causes is we have the most of it. So we have astronomical amounts more carbon dioxide than we have these other ones. So even though these other ones are bigger problems, carbon dioxide has the sheer volume. There's just too much of it. This is the big issue. Methane gas, CH4, 84 times more warming potential than carbon dioxide. So methane is a problem. Okay, that's a big problem. We overproduce methane, we're going to have issues. Nitrous oxides, 264 times more warming potential than carbon dioxide. Remember from our earlier chapter, chlorofluorocarbons or hydrochlorofluorocarbons, same difference. Those are some of the worst, 10,800 times more warming potential than carbon dioxide. So it's just showing you, and that's over 20 years, over 100 years, it's even worse. Because some of these stay up in the atmosphere for a long time and don't break down, and they become major issues down the road. Greenhouse gas concentrations. Well, this graph here shows you where everything used to be. You know, red is CO2, methane is green, nitrous oxide is blue. And then what happened? Industrial revolution. Okay. Industrial revolution, late 1800s, and boom, all of those went up. Everything went up in quantities. Basically, we've been monitoring this, and we have data that goes back about 800,000 years. You're going to see 800,000 years keep popping up, and that's how far back our data goes. And I'll explain to you later in a different lecture why we have data that goes back 800,000 years. They measure the atmospheric carbon dioxide in parts per million. You're going to see that term. The magic number we never wanted to exceed is 400, and now we've exceeded it. We average above 400 parts per million daily now. When I first started teaching this class, we were in the upper 300s, and the whole goal at that time was to never reach 400, and we have reached 400, and we are above 400 now. Where does most of this carbon dioxide come from? Burning a fossil fuel. Simple. Burning oil, burning coal, burning natural gas, carbon dioxide is made. So the big issue, what's happening with climate, is we are taking Earth's climate and we are shifting it back, basically. What we're saying is we didn't have humans around 800,000 years ago. Humans were not around. Primitive humans go back about 200,000 years. So let's go back even 600,000 years before humans. We are shifting our climate patterns back in time to about 800,000 years ago, where climate was different as a result of the different amounts of these specific gases. So what is happening? Humans are really messing with climate. We are shifting the percentages of and the quantities of what we have in the air, and it is not making things better here. It's making things warmer. What is happening? Well, because of carbon dioxide, here's another problem. So we're burning. We're also deforesting, right? So we're removing what are called sinks or reservoirs of carbon, and we're cutting them down. And that releases a lot more carbon dioxide to the air. All right. So now plants can't do photosynthesis to remove it as much if we keep cutting them down. And we're clearing them because we want more space for land to do different things that humans may need done. Methane is a big one. We grow more, we have ranchers, we have food. People like meat on our planet. Livestock production, raising livestock is a big methane producer. And the more meat we eat, the more methane that we will be producing. A lot of the methane is released in when bacteria break down organic matter in landfills. Growing rice also releases methane gas. That's one that people don't realize. The more rice we eat in these rice paddies, there's methane being produced below ground by bacteria that are in these rice paddies. So people don't even think of that. Like certain foods we eat may be related to methane. So meat and rice and things of that sort. Nitrous oxide, well, a lot more cars, also back to feedlots, and a lot of synthetic fertilizers have these nitrogen compounds in them. So these nitrous oxides are a problem, and we're making more of them. And ozone, okay, where's ozone? Well, we learned in our last chapter that ozone is being made as a result of all these other things reacting in the presence of light. That's photochemical smog. So ozone is a greenhouse gas, and it is increasing in numbers as a result of the smog and all the other things that are being produced. What is this picture showing you? It's there's a lot of numbers on these, and these numbers are confusing, but the reason I'm showing these pictures is these types of diagrams show up on AP tests where they have numbers and you're like going to be confused. This one has to do with carbon dioxide and the billions of metric tons. So balance would be, they're saying per year, 450 billions of metric tons of carbon dioxide can be basically, then this is the land versus the ocean, 440 billions of metric tons are going to be sequestered by photosynthesis, and then respiration is going to release about that much. And the red is showing you human things. The green is natural causes. Okay. What they're showing you here is what happens in the ocean and what happens on land. And overall is the important thing. The net, that's overall. Overall, about 15 billion metric tons of carbon dioxide are entering the atmosphere each year. Okay, so you have a balance situation. You want to sequester and release about the same, and then you have balance. Because of human activities, we are not absorbing and sequestering the same. We are overall netting 15 extra entering the atmosphere. Doesn't sound like much, 15 billion metric tons, but over years and years and years and years, it starts adding up and we start shifting the proportions of the atmosphere. Aerosols. What are aerosols? Well, we always think of them as things in spray paints and cans and things of that sort, but aerosols have a technical definition in environmental science. They are things that have an albedo, an ability to reflect light. And what they do is they generally reflect light away from the earth, keeping it cooler. So some people will argue that there are instances that actually cool the earth, and there are instances that cool the earth. For example, if a volcano erupts and it releases a bunch of sulfur-based compounds in the sky and ash too, some of these things will end up and they'll create a aerosol layer. All right. So albedo is the ability to reflect light. Well, if light hits these aerosols and gets reflected away from the earth, overall we can have a net cooling effect due to aerosols. After massive volcanic eruptions, you have clouds, you have other things in the sky, so they can block or be aerosols. Just so you know, ash in the sky, okay, can actually cause some warming if they get heated up because they're darker in color. So it's very complicated. It's not some simple thing that some things cool, some things warm, but there are countering effects of each other, which is what you need to understand about climate. And aerosols are believed to have a cooling effect. I've had students in the past ask me, well, why can't we just release aerosols and not have the earth as cool? It's not so simple. We can't just control where those aerosols are. There's wind patterns. There's things that are going to carry them to different places. They'll impact some places way more than others because of the way patterns and air moves around the planet, wind. So it's not as simple as just releasing aerosols into the sky. All right. We're going to stop there with this lecture.